Let us continue intermolecular forces. Now we will take a helium gas in water. Helium gas in water we will take. Sir, what type of intermolecular force possible here? That we will see. Now, first we will take water. Water in the central atom oxygen, surrounding atoms hydrogen atoms, and oxygen is having two lone pairs. We know that hydrogen is less electronegative than oxygen. Therefore, hydrogen partial positive, oxygen partial negative. Sir. Now we will take helium. Helium configuration is 1s2. Now helium nucleus we will take and 1s2. Spherical and symmetric we will consider. Spherical and symmetric. 1s2 is spherical and symmetric. Okay. Now this positive charge will attract this electron cloud. This positive charge will attract this electron cloud. Due to that, what will happen? This electron cloud moves towards that side. That side in the sense that side in the sense this side. Okay. So this electron cloud is moving to this side. So this electron cloud is moving to this side in the sense here electron cloud becomes less probability. Here probability of electron cloud becomes high. Okay. So now what will happen? We'll see. Now in water this is partial positive, it is partial negative. This helium becomes what in the sense helium electron cloud becomes like this. So in this helium electron cloud, here probability of electron cloud is high. Here probability of electron cloud is low. Okay, here probability of electron cloud is low, here probability of electron cloud is high. Therefore this end is partial negative, this end is partial positive. This end we can say partial negative, we can say this end we can say partial positive, we can say. This partial positive charge will attract this partial negative charge. Therefore, it is intermolecular force. What type of intermolecular force? In the sense, it is dipolar species. It is a dipolar species. Here also dipole is created. But here dipole is created because of which? Because of this. Therefore, here dipole is created because of induced, which water. Therefore, it is induced dipole. So here attraction possible between dipole and induced dipole. This type of attraction is one type for intermolecular force. So in the intermolecular force, this type is what in the sense a dipole induced dipole attraction. This dipole in the sense it is polar molecule. Induced dipole in the sense it is non-polar molecule. So dipole induced dipole attraction is possible in a polar molecule and non-polar molecule. So this type of interaction is possible between polar molecule and non-polar molecule, we can say. So between polar molecule and non-polar molecule, what type of intermolecular force is possible? Dipole induced dipole is possible. Dipole induced dipole attraction is possible, sir. Now here interaction energy is directly proportional to 1 by r power 6. R is called distance between two molecules. We can say. Okay. Now we will go for next type of intermolecular force that we will take. Now we will take a HF molecule. We will take. In the HF molecule, fluorine is having more electronegative than hydrogen. So fluorine will have partial negative, hydrogen will have partial positive. Now I will take another HF molecule. Here fluorine has a partial negative charge, hydrogen has partial positive charge. Now This is dipole, it is another dipole. Between them attraction is possible. This attraction is called dipole attraction. Sir, but this dipole attraction is coming under a special category. What is that? Now in this species, that means we can consider it is as a group or this is as a molecule. In this molecule, this is high electronegative atom. In this species in the sense it may be group or molecule, anything we can consider. Sir, here it is molecule, here it is a hydrogen. This hydrogen is attached to high electronegative atom, is attached to high electronegative atom. High electronegative atom, it is high electronegative atom, it is hydrogen, it is attached to high electronegative atom. Between them attractive force is possible. This attractive force is called hydrogen bonding. This is called what in the sense? Hydrogen bonding. So hydrogen bonding is one type of intermolecular force. It is possible between what in the sense? High electronegative atom of a group or a molecule, and hydrogen is attached to high electronegative atom of another group or a molecule. Between them force of attraction is possible. That attraction is called hydrogen bonding. Sir, in HF hydrogen bonding is possible. Sir, now we will take water. We will take, I am taking water. In water, what is the intermolecular force that we will see? It is a water. Here hydrogen is having partial positive charge, oxygen is having partial negative charge. Another water molecule I will take. Here partial charges will give oxygen partial negative, hydrogen partial positive. Between, now it is hydrogen attached to high electronegative atom. Okay, it is high electronegative atom. Between them attraction is possible. That is called hydrogen bonding. This is called hydrogen bonding. Sir, next we will take, now we will take ammonia. Ammonia we are taking. In ammonia, hydrogen is having partial positive, nitrogen is having partial negative. Another ammonia molecule I will take. Here we will give partial charges. Now in this molecule or in this group, hydrogen is attached to high electronegative atom. That hydrogen will take. In this group or in this molecule, high electronegative atom will take. Between them attractive force is possible. This is called what in the sense? Hydrogen bonding. Sir, next molecule we will take. Next we will take a molecule called so and so. It is called para dihydroxybenzene. Sir, like this only another molecule I will take. Another molecule I have taken. Now this is hydrogen. It is attached to high electronegative atom. In this group, high electronegative atom is this. Between them attractive force is possible. This is called hydrogen bonding. This is called hydrogen bonding. Okay, sir. Next we will take a molecule like this. It is benzene. Here we will consider OH group. Here we will consider C double bond OH aldehyde group. Now this is hydrogen. This hydrogen is having partial positive charge because it is attached to high electronegative atom. Okay, so in this group hydrogen is attached to high electronegative atom. It is a group. In this group, this oxygen is I electronegative atom is having partial negative charge. This group present in this molecule, this group also present in this molecule. Both groups present in within a molecule. So between them, attractive force is possible. That is called hydrogen bond. So here, in this case, this HF is one molecule, this HF is another molecule. Between these two molecules, hydrogen bonding is possible. This is called intermolecular hydrogen bonding. Intermolecular hydrogen bonding. Intermolecular hydrogen bonding is nothing but hydrogen bond between two molecules. It is water molecule. It is another water molecule. Between two molecules, hydrogen bond is possible. Therefore, it is called intermolecular hydrogen bonding. It is ammonia molecule. It is ammonia molecule. Between these two molecules, hydrogen bonding is possible. Therefore, it is called intermolecular hydrogen bonding. It is a para-dihydroxybenzene. This is para-dihydroxybenzene. Between them, between these two molecules, hydrogen bonding is possible. It is called intermolecular hydrogen bonding. Now, we'll take it is one molecule. In this one molecule, this is one group. This is another group. Between these two groups, hydrogen bonding is possible. That means here hydrogen bonding is possible between two groups within a molecule. It is called a intramolecular hydrogen bonding. Intramolecular hydrogen bonding. Intramolecular hydrogen bonding we can say. So in hydrogen bonding, two types we said. One is inter, another one is intra. Two types of hydrogen bonding is possible. So, due to hydrogen bonding, what are the effects? What are the favorable things? What are the unfavorable things? What will happen due to this? That we'll see. Now if you see, regarding solubility, if you see, like dissolves like dissolves like. That means polar substance dissolves in polar solvent. Non-polar substance dissolves in non-polar solvent. So, now we will take alcohol. We will take for alcohol group is ROH. This ROH, for this what is example in the sense in the place of R we will take suppose methyl. We will take methyl and OH will. Now this oxygen electronegativity is 3.5, hydrogen electronegativity is 2.1. Difference is much is there, therefore it is a polar. Hydrogen partial positive, oxygen partial negative, therefore it is polar. Now this carbon and hydrogen, carbon 2.5, hydrogen 2.1, electronegativity difference is less, therefore this part is called hydrocarbon part. Hydrocarbon part in the sense that is having hydrogen and carbon. This is almost non-polar. Almost non-polar we can say. Now we will take water. Water is what in the sense polar solvent. Water is polar solvent. Water is polar solvent. Now this polar group dissolves in this polar group because of attraction, dissolves. So this OH group dissolves in water because of what in the sense attraction. This non-polar group repels this polar group because repels due to that it is not dissolving. It is not dissolving. It is repelling. Therefore, it is not dissolved. Okay. If this is more pronounced than this, then this molecule dissolves. If it is more effect when compared to this effect, then it is not dissolved like this. Okay. So now regarding this alcohol in water, how it will be there in the sense lower alcohols are soluble in water. Lower alcohols are soluble in water, we can say. Lower alcohols in the sense this R group will be lesser in size. This R group will be lesser in size. Okay, if R group is lesser in size, then we can say lower alcohols, that is soluble in water. That means this factor is dominant when compared to this factor. So lower alcohols is soluble in water because of what? Because of hydrogen bonding. So next we will take a next I will take HF and HCl. Now this molecular mass we will see this molecular mass is high when compared to this molecular mass. Generally molecular mass is high in the sense boiling point will be high. It is the general trend. Okay. Generally molecular mass is high in the sense boiling point will be higher. It is a general concept. So when you are seeing about boiling point, how to say which is having higher boiling point and which is having lower boiling point, in the sense you see the molecular mass. If molecular mass is high, then you say that is having higher boiling point. Okay, then only rest of the factors we have to consider. First we have to consider what, in the sense molecular mass. So melting point means how to say? Melting point in the sense symmetry of the molecule we have to see. If symmetry of molecule is high, then extent of close packing will be high, then melting point will be high. So for saying melting point, we have to see symmetry. Sorry. So boiling point means we have to see molecular mass, melting point means we have to see symmetry. Okay. Next. In this molecular mass, some exception is there. So general is what? Higher the molecular mass, higher the boiling point. In that exception is there. What is the exception? Means hydrogen bonding comes under exception to this. So hydrogen bonding comes under exception to this. Okay. So in this one, what is the exception, in the sense hydrogen bonding? Hydrogen bonding. Therefore, what is the experimental point says regarding this boiling point? We'll see. Experimental boiling point is what? HF greater than HCl. It is experimental value. So this is not in accordance with the experimental then. Okay. So generally molecular mass we have to see to say the boiling point, where exception hydrogen bonding is the exception. So HF is HF boiling point is greater than HCl boiling point. It is experimental says. Experiment says like this. Why is it so? We'll see. Now HF in liquid state, and in vapor state, hydrogen bonding is possible. Hydrogen bonding is possible. But HCl, no hydrogen bonding. HCl in the sense hydrogen bonding not possible. For HCl, hydrogen bonding is not possible, but HF in the sense hydrogen bonding is possible. Sir. So how the hydrogen bonding is in HF? In HF hydrogen bonding is there. How it is there, that we will see. Now we will take HF molecule. We have taken HF molecule. We are taking a HF molecule like this. Okay, we have taken HF molecules. Now we know that fluorine is having partial negative charge, hydrogen is having partial positive charge, therefore hydrogen bonding. Here also hydrogen bonding. So between fluorine and hydrogen, what is possible, in the sense hydrogen bonding is possible. Hydrogen bonding is possible like this. It is going for hydrogen bonding with the neighbor. It is going for hydrogen bonding with the neighbor. So like this, hydrogen bonding is possible. Due to hydrogen bonding, this HF molecule is arranged in a zigzag manner. So in liquid state, hydrogen bond continues like this. Okay. In liquid state, hydrogen bonding is continuing like this. What about in vapor? In vapor, how the hydrogen bonding is there, that we will see. Now we will take HF. Okay, we have taken HF. In vapor, how the hydrogen bonding will be there? In vapor, in the sense, it may exist as hexamer. Otherwise, other possibility also there. Sir, first hexamer it is possible. Sir, one nitrogen bonding, second molecule, third molecule making hydrogen bonding, fourth molecule making hydrogen bonding, fifth molecule is making hydrogen bonding. Now, here how many molecules means 1, 2, 3, 4, 5, 6. Therefore, hexamer. Next, here no hydrogen bonding. Here hydrogen bonding, second hydrogen bonding, third hydrogen bonding, fourth hydrogen bonding, fifth hydrogen bonding. It is one hexamer. Hexamer in the sense, now at this place, no hydrogen bond. No hydrogen bond. Okay, it is hexamer. Even tetramer is possible. In the vapor state, what is possible in the sense tetramer? Tetramer is possible. We are writing a HF like this. Okay, now we will see the hydrogen bonding. So 1, 2, 3. Okay, it is first molecule, second molecule, third molecule, fourth molecule. Hydrogen bonding we have given tetramer. Here don't give hydrogen bonding because tetramer. Okay, so here hydrogen bonding will give 1, 2, 3. So the one molecule, second molecule, third molecule, fourth molecule, hydrogen bonding is there. Here no hydrogen bonding. Here hydrogen bonding. Here hydrogen bonding. Okay, so 1, 2, 3, 4. So this hydrogen bonding will not be there. Here no hydrogen bonding. Next, here hydrogen bonding, next molecule hydrogen bonding. Okay, so tetramer means have we got an idea? Here hydrogen bonding not present, no hydrogen bonding. So in the vapor state, HF exists as a hexamer or tetramer or trimer, dimer, like this. Many possibilities are there. Any of hydrogen bonding is possible even in vapor state. Sir, what about HCl? No hydrogen bond. Okay, sir. Now, to convert this liquid into vapor, we have to bring this liquid to certain temperature. That temperature is called boiling point. At that boiling point, liquid is converting into vapor. So, when liquid is converting into vapor, is there any necessity of breaking all the hydrogen bonds? No. Only few hydrogen bonds, if it is breaking, then liquid is converting into vapor. Therefore, the boiling point of this boiling point of HF is what, in the sense some value is there. Now we will see HCl. HCl. Here in HCl, no hydrogen bonding. No hydrogen bonding. Then what type of intermolecular force possible, in the sense dipole-dipole attraction. Dipole-dipole attraction. So HCl liquid is having dipole-dipole attraction. Hydrogen bonding is not there. Sir, intermolecular force strength we will see. Strength, if you see, HF hydrogen bonding is greater than HCl dipole-dipole attraction. Sir, this liquid we are converting into vapor. This liquid we are converting into vapor, for which we have to bring this liquid to certain temperature, that is called boiling point of HCl. At that temperature, this HCl liquid is converting into HCl vapor. Okay. So HCl is having certain boiling point, HF is having certain boiling point. Here, in this case, to convert liquid into vapor, which intermolecular force should be broken? Dipole-dipole attraction should be broken. But in HF case, which intermolecular force should be broken? Hydrogen bonding should be broken. Hydrogen bond strength is greater than this dipole-dipole attraction. Therefore, here intermolecular force of attraction is dipole-dipole attraction, which is lesser in strength. Therefore, boiling point is low. In HF, intermolecular force is hydrogen bond, that strength is high. Therefore, we have to provide a higher temperature. So here boiling point is high. Okay. So boiling point of HF is greater than that of HCl. Why? Because HF is having intermolecular force hydrogen bonding. HCl is having intermolecular force dipole-dipole attraction. Therefore, HF requires more energy. At higher temperature, it is undergoing vaporization when compared to HCl. So HF boiling point is greater than HCl boiling point. Okay. So why boiling point of HF is greater than that of HCl? In HF, hydrogen bonding is there. In HCl, hydrogen bonding not there. Okay. So next we will take a water and H2S. We will take. We will take what in the sense water and H2S. Boiling point of water is greater than boiling point of H2S. What is the reason? We will see. In water, hydrogen bonding is possible. Hydrogen bonding is possible. In H2S, no hydrogen bonding. It is a reason. In water, hydrogen bonding is possible. In H2S, no hydrogen bonding. Sir. Next, we will see boiling point of ammonia and pH3. We will see. pH3 is called phosphine. Why boiling point of ammonia is high means hydrogen bonding is possible in ammonia. In phosphine, hydrogen bonding is not possible. In phosphine, hydrogen bonding is not possible. Sir. Next, boiling point of water and HF we will see. Boiling point of water and HF. Okay. Boiling point of water is greater than boiling point of HF. In water, hydrogen bonding is possible. In HF also hydrogen bonding is possible. In water, hydrogen bonding is there. In HF also hydrogen bonding is there. Okay. Experiment says that boiling point of water is greater than that of HF. Sir, how to explain and what are the points we will see. Sir. In water, hydrogen bonding is there. HF also having hydrogen bond. Sir. Now we will take one water molecule. For water molecule, we will give partial charges. Hydrogen partial negative, oxygen partial positive. Hydrogen partial negative, sorry. For hydrogen, we have to give for hydrogen, we are giving partial positive, oxygen, we are giving partial negative. Here, partial positive, partial negative. This hydrogen is making hydrogen bonding with another water molecule. This hydrogen is making hydrogen bonding with another water molecule. This partial negative charge is making hydrogen bonding with another water molecule. This partial negative charge is making hydrogen bond with another water molecule. Therefore, one water molecule makes four hydrogen bonds with neighboring water molecules. Okay. So we said one water molecule is making four hydrogen bonds with the neighboring water molecules. So what about HF? That we will see. In HF, this HF if you take, this side one hydrogen bond, this side one hydrogen bond. Okay. So one HF molecule makes two hydrogen bonds two hydrogen bonds with neighbors, neighboring HF molecules with the neighbors. So one HF molecule makes two hydrogen bonds with the neighbors. This is one HF molecule. This one HF molecule makes two hydrogen bonds with the neighbors. But water, if you see, one water molecule makes four hydrogen bonds with the neighbors. So, next, we will convert water liquid into water vapor. In vapor, no hydrogen bonds present. In vapor, no hydrogen bonds present. That means when you are converting liquid into vapor, we have to break all hydrogen bonds in liquid water, then only we will get water vapor. So what about HF? That we'll see. Liquid HF is having hydrogen bonding like this. Vapor HF means it is existing as hexamer, otherwise tetramer. That means even in vapor state hydrogen bonding is there. So liquid HF is having more number of hydrogen bonds. Vapor HF is having less number of hydrogen bonds. That means when you are converting liquid into vapor, some of the hydrogen bonds should be broken, but not all. Hydrogen bonds. Some of the hydrogen bonds should be broken, but not all the hydrogen bonds. We have to break some of the hydrogen bonds. We need not break all the hydrogen bonds. Okay, so some of the hydrogen bonds we have to break, then this HF liquid is converting into HF vapor. So next we will see water molecular mass is 18, HF molecular mass is 20. So what is experimental fact? Experimental fact says that boiling point of water is greater than boiling point of HF. For this water, what is the suitable reasoning? That we will see. Okay. Now, one water molecule makes four hydrogen bonds with the neighbors, and to convert liquid into vapor, all the hydrogen bonds we have to break in the case of water. So, in the case of HF, each HF molecule making two hydrogen bonds. To convert liquid into vapor, we have to break some of the hydrogen bonds, but not all. Therefore, which requires more energy to convert liquid into vapor? No doubt water, but not HF. Therefore, boiling point of water is greater than boiling point of HF. Okay. So, we have given a suitable explanation for this experimental fact. Sir, next we will see. Molecular mass of water is low, molecular mass of HF is high. So using this molecular mass, we cannot explain what in the sense experimental boiling point. So we need not take. So next point we will take. Now in water in the sense oxygen electronegativity is how much in the sense this oxygen electronegativity is 3.5, hydrogen is 2.1. Therefore electronegativity difference what we will see. So in water OH bond is there. This electronegativity is 3.5, this electronegativity is 2.1. Therefore, electronegativity difference is how much in the sense that is 1.4. In HF will take fluorine 4, hydrogen 2.1. Therefore, difference is how much in the sense 1.9. Therefore, here partial negative charge possible, here also partial negative charge possible, here partial positive, here partial positive. This magnitude if you see less, this magnitude if you see high, because difference is more. Therefore, it is making hydrogen bonding no, that strength will be high. It is making hydrogen bonding no, that strength will be low. So, if strength of hydrogen bonding is high, then boiling point should be high, isn't it? So, we have to break the hydrogen bonding no. We have to break the hydrogen bonding means we have to supply the energy. We have to supply energy in the sense if strength is more energy we have to supply, isn't it? So this strength is more, so more energy we have to supply. Therefore, this boiling point is more when compared to this. But experimental fact is opposite. Therefore, it is not suitable reasoning for the experimental fact. We cannot say that HF strength is HF hydrogen bond strength is less. We cannot say when compared to water. You see more only. But this fact, this reason is not suitable for experimental fact. Therefore, we should not consider this fact. We should not consider in the sense we should not say this point in order to explain this, in order to explain this boiling point. Okay, so to explain boiling point of water is greater than HF, what point we have to say? One water molecule makes 4 hydrogen bonds with the neighbors, and on converting liquid water into vapor water, all the hydrogen bonds we have to break. Then in HF, each HF molecule is making 2 hydrogen bonds. To convert liquid into vapor, we need not break all the hydrogen bonds. Some of the hydrogen bonds only we have to break. Therefore, HF is having lesser boiling point. Therefore, HF is having lesser boiling point, whereas water is having more boiling point. Like this we can say. Okay. Therefore, we can say HF is having lesser boiling point. Okay. So, this point we are saying that HF is having lesser boiling point. Okay. HF is having lesser boiling point, whereas water is having higher boiling point, we have to say. Okay. So, don't say this reason. If you say this reason, what will happen? Strength is more means more energy we have to supply. Then boiling point is high, no. But experiment says it is having low boiling point. Therefore, don't say this point. Okay. That means this point is, this point we cannot say incorrect. This point is correct only. This point is correct only, but it is not suitable reasoning for a boiling point of water is greater than HF. For that, it is not suitable reasoning. Okay. That means from this, what we are coming to know in the sense, we have to know, we should know experimental fact. For the experimental fact, we have to give the suitable reasoning. We have to give all the reasons we cannot take. First, we have to see experimental fact. Then only which reason is suitable, that we have to see and that we have to apply. That means experimental fact we should know in the sense that is knowledge part. So we have to study. We must study. Then only we can know experimental factor. Then only we can say what is the suitable reasoning. Okay. So the understanding part alone is not enough. Experimental fact and knowledge is first, then understanding, and then application. Like this we have to go. That means we have to study, then only we can attempt objective type of questions. Sorry, okay. Next we will see boiling point of ammonia and HCl. We will see boiling point of ammonia is greater than boiling point of HCl. So what is the reason? We will see ammonia is having hydrogen bonding. HCl is not having hydrogen bonding. No hydrogen bond. Okay. Here HCl in the sense it is not aqueous solution of HCl, only HCl. Okay. So here hydrogen bonding not there, here hydrogen bonding is there. Okay. What is the molecular mass? That we will see. Ammonia is 17, but HCl is 35.5. So molecular mass we should not consider to explain this boiling point. We have to consider only hydrogen bond to explain this boiling point. So next we will take. Next we will consider so and so. This is a hydroxy group. It is benzene group. This is what in the sense aldehyde group. It is called para hydroxy benzaldehyde. So another molecule I will take. I have taken another para hydroxy benzaldehyde. Okay. This is what in the sense para hydroxy benzaldehyde I have considered. So next I will consider. This is what in the sense hydroxy group. This is what in the sense aldehyde group. It is a orthohydroxy benzaldehyde. Another one we will take. Another compound we will take. Here a OH group. Here a aldehyde group. It is what in the sense orthohydroxy benzaldehyde. Okay. It is para hydroxy benzaldehyde. It is orthohydroxy benzaldehyde. Okay.